Okay, so we have our last talk for today. Evgeny Smirnov will talk about polytopes and K theory of toric and flag varieties. Женя?
Thank you very much. And Pasha, thank you for introduction. And it's really great pleasure to be here. And thank you, big thank you to all the organizers of this event, as well as the previous 2 weeks event. Bart, Pasha, Anton, Zhenya, you guys doing great job. Thank you so much. So today I will speak about polytopes, about some approach to computing cohomology, K theory of flag and toric varieties using polytopes. Yeah, in a sense, this will be, well, the objects I will consider in the last part of my talk will be the geometric counterparts that Gleb has hidden from us in his talk. So we'll solve the same problem, but from kind of another perspective and similar problems. And yeah, this is joint work with Leonid Monin from Lausanne, and the short announcement was published in Séminaire Lotharingen de Combinatoire in last year, but the full text is still in the process of writing. So hopefully it will appear soon. So let me start with certain purely algebraic construction, which is due to Alexander Pukhlikov and Askold Khovanskii. So part one, purely algebraic construction. Well, let us take a finite dimensional vector space, let's say over R. Let V be R to the power, let's say n. And, we can consider polynomial functions on this space. So as opposed to the previous talk, my talk requires some preliminaries, so you're supposed to know what a polynomial is, right? Okay, so consider a homogeneous polynomial f, x1, etc., xn, homogeneous of degree d on this, so v into R, homogeneous of degree, let's say d. And given such a polynomial, I will produce a ring, an R algebra, in the following way. So I can take my V and I can take differential operators on V with constant coefficients. So these are some fellows like d over dxi, and everything obtained by multiplying them and taking their sums with real coefficients, but not with functional coefficients. So I don't have things like x times d over dx. So let me take the ring diff V, which is R. So it is also isomorphic to the ring of polynomials in the same number of variables. And inside this ring, well, I can apply differential operators to various polynomials, for instance, to f. And inside this ring, I can take the annihilator of my f. These are those polynomials, those differential operators, d such that df is identically 0. And this is obviously an ideal. And the quotient, which I will denote by AF, by definition will be the quotient of these differential operators by the annihilator of f, is a ring which I will, is the ring which I will produce starting with f. So here's the construction of a ring for, given a homogeneous polynomial and variables, I produce a ring. And this ring, is this clear so far? Okay, so this ring has some nice properties. Well, here are some of them. So properties of AF. First of all, it's a graded R algebra. With grading of depth from 0 to D, right? Graded R algebra. Okay, so second property is that, well, the lowest degree is obviously one-dimensional, the zero component. These are constants from our differential operators ring. And the top component is obviously one-dimensional as well, right? There is only one after proportionality such operator that it gives some non-zero constant while applied to f. So AF0 is isomorphic to AF top is isomorphic to R. So these components are in a sense symmetric, right? And even more, there is also a pairing between, well, the kth component from the left and kth component from the right. So I can define the following pairing. So AF K times AF D minus K into R. Yeah, and well, this is graded R algebra, and it is finite dimensional. Yeah, why is it finite dimensional? Because the differential operator of sufficiently large degree will cancel my f. So this there is pairing like d1, d2 goes into d1, d2 applied to f. So this is a non-degenerate pairing. Why is it non-degenerate? Because, because for each, okay, let me leave it as an exercise, as an easy exercise. So yeah, given D2F, you'll need to find D1 such that the result is non-zero, and it's always possible. So part 4, fourth property is that this ring is generated by the component of degree 1 as an algebra. So AF is generated by the first degree component. Okay, so these are very nice properties of this ring, and in a sense they characterize this this class of rings uniquely. What do I mean by that? I mean the following theorem. Theorem by Pukhlikov and Khovanskii. '92. So given ring A satisfying 1, 4, so a graded ring with such a duality with 0 and top component being one-dimensional and generated by the top by the first degree component, such a ring has the form given on the top blackboard. So this ring is obtained as a f for a certain f. So A is isomorphic to AF, where F is the following. It's the following map from A1 to R, where an element of degree 1, of grading 1, goes to its dth power, goes to its top power, and top power is one-dimensional, right? So A to the power D, which can be viewed as an element from here. So this is maybe bad phrasing. So this is a D, which is isomorphic to R. Okay, so I can, so if I know that my ring is generated by the first degree component, I can consider the following polynomial, and this will be the polynomial that will produce this ring as a result of this construction. It's really easy, but where in nature do such rings come from? What are these rings with properties 1 to 4? Well, properties 1, 2, and 3 recall us cohomology rings of smooth varieties, smooth manifolds if you prefer the differential geometric setting. But yeah, so this thing is then Poincare duality. And this is kind of special property that not all, of course, not all smooth manifolds have. This is a property that the cohomology ring is generated by the divisors, by the Picard group. So well, there are some classes of varieties with such a property, and one of them is given here, toric varieties. So let me give some sort of mini course in the theory of toric varieties. So these are homology rings of toric varieties are of such a form if X is a toric variety. Well, is toric variety. Well, I'll consider varieties over complex numbers, and what is a toric variety? Well, what is a torus, first of all? Torus for me is C star to the power to the power D. So T, this thing is an algebraic torus, multiplicative group of C. And well, for me, all toric varieties will be projective, and mostly I'll be working with toric varieties embedded into projective space. So it's usually called polarized varieties. So projective, polarized, projective. And so I consider T, well, basically embeddings of this torus into projective space. So I can say that I have T embedded into, well, T acting on some, yeah, let's say that if T operates on some X with an open orbit, and X is irreducible normal projective variety. So my X is embedded into Pn. Well, this means I'm dealing with a toric variety. So how to? Well, the main benefit of work with toric varieties is that they are very combinatorial. You can encode pretty much everything about them just in the language of polytopes or in the language of fans, which is in a sense dual but pretty much the same. So so the geometry of a toric variety is governed by a certain integer polytope. And let me give the construction other way around, from polytope to a toric variety. So let P in Zn and Rn be a polytope. Well, let me write something like this in the plane. This is X, this is Y. So given such a polytope, I will construct a toric variety. How will I do that? So let me take all integer points. Well, let me denote the number of integer points by n plus 1, capital N plus 1. And, well, because I want to projectivize it and get this space. So that's where plus 1 comes from. So let me say that my integer points will be responsible for homogeneous coordinates in this space. And given each point, it has some x component and y, some x coordinate and y coordinate. I can take t1 to the power x coordinate and t2 to the power y coordinate. So this will be 1, this will be t1, t1 squared, t2, t1, t2, t1, t2 squared, t1, t2 squared. And let me say that I will just send my point of my torus, t1, t2, maps into 1, t1, t1 squared, t2, t1, t2, t2 squared, t1, t2 squared. So this sits inside P6, right? And let me take the closure of a certain point with non-zero coordinates. Let me say I'll take the closure of point 111, etc. So T applied to the point 1 all once, its closure will be my X. That will sit inside P6, so it will be equipped with the action of the torus, and well, this will be the so the closure. So it will have T as its open orbit, right? That's how it works. And here's some dictionary. So what I'm saying now is that this polytope, this integer polytope, knows everything about my variety. Namely, the T orbits in this variety. So the I have open orbit and I can degenerate to the boundary. So the orbits of the boundary are governed by faces of smaller dimension. So dictionary toric varieties, polytopes. So T orbits of dimension K, this is a K-dimensional face. Toric variety X and polytope, let's say, polytope P. So face of dimension K, face of the same dimension. And well, if you want to intersect two such orbit closures, you'll get, well, this T-orbit, I must say here, closure of dimension K, this will be face, and if you want to, say, to intersect two such orbit closures, you'll get a face of smaller dimension that will correspond to the intersection of these faces. So very nice setting. And one more thing is that from this polytope you can say whether your variety is smooth. So X is smooth if and only if P is integrally simple. Simple polytope is, well, it's a polytope with few faces or few edges meeting in one vertex with as little edges as possible. So tetrahedron or a cube are simple because in every vertex you have three faces meeting, and an octahedron is not. There are four of them, right? So, and integrally simple is the following. So for each face, you can take you can take the normal vector of smallest length. So the primitive vector, primitive normal vector, and if in every vertex, well, so for every vertex you'll get as many vectors, as many normal vectors as the dimension of your space, since you have that many faces. And if they form a basis, it means this is an integrally simple polytope, the basis of my lattice Zn. So, for example, this corresponds to a non-integrally simple polytope because I have a vector 0, 1 and a vector 2, 1. And they do not generate the whole lattice, only half of it, right? Only vertices with nodes with even x coordinate. But yeah, so this is not a smooth variety. So what else can I say is that, well, sometimes I can obtain the, well, different embeddings of the same variety, so to say. So when do I obtain this? When so x p is isomorphic to x p prime p or tilde as a T variety, even only if p and p tilde have the same normal fan. P and p tilde have the same normal fan. So what is a normal fan? Well, I basically wrote it here. So let me draw this picture again, and let me draw a larger picture. So for each vertex, for each face that I can consider the normal primitive vector, right? So this gives me a fan. and these so this vertex corresponds to this cone, to that cone. Well, so here the dimension kind of is inverse, right? So what you have, so zero-dimensional thing here becomes top-dimensional cone of this polytope and other way around. So we can, instead of speaking about polytope, we can speak about its fan, and so sigma, normal fan of P. So this says that I get the same variety if the geometry of my polytope is the same. So I can move the faces around parallel to themselves without just changing the combinatorial structure of this polytope, and I'll get the same embedding. So, what do I? So what do I have? I need to. So, given a fan, how do I construct a polytope? I need to specify the so-called support numbers. So let me say that, given the origin, the 0 point, I can take h1, h2, h3, and h4, some positive numbers, so I will call them support numbers, h1, h2, h3, h4, support numbers. And given a fan and a bunch of support numbers, eventually I get a polytope, if I'm lucky. Sometimes I won't get a polytope, so imagine that like your h1 is really, really big, then these two faces intersect before they meet this face, right? So you'll get something like something ugly, which is not a real polytope, something like that. But if you're lucky, you get an actual polytope. Well, you can say that these polytopes live inside a cone, so you can add them by Minkowski. So P sigma plus cone of polytopes with fan sigma. Or, if you wish, you can, well, cone is not as nice as a vector space, so you just can formally say that, well, you allow your h's to be any combinations. So you'll get some bigger vector space, P sigma, and this will be the space of virtual polytopes with this normal fan. So virtual polytopes with fan sigma. Okay, so given these, well, I can say that my embedding, well, in geometric terms, my embedding is a bunch of support numbers. So yeah, my divisors correspond to facets. Orbit closures of codimension 1 corresponds to facets of my polytope or to rays of my fan. So I can say that so that a polytope P with support numbers H in geometric terms, this condition corresponds to the fact that P sigma plus, yeah. In geometric terms, this corresponds to the fact that the divisor h1 d1 plus etc. plus h whatever is the number ds in X is ample or very ample, which is the same in this case. Okay, so this is the divisor dh, and this divisor defines me the embedding of the projective embedding of my space of my variety X. So now I would like to have a construction of well, as I told you, this homology ring is a ring of such a form for some mysterious polynomial f. And let me now show you what this polynomial f is. It has very transparent geometric meaning that people learn about in, well, I think first grade. Yeah, so mystery aside, this is the volume of this polytope. So here's a theorem by essentially this is a theorem due to Kushnerienko, and in this version it was modified by David Bernstein and Askold Khovanskii. So theorem, I'll put these three names here: David Bernstein, Anatoly Kushnerienko, Askold Khovanskii. If I take a T invariant divisor, well, let's say ample divisor, dH, and I consider it self-intersection number. I just multiply its class by itself d many times to get a number. So T d to the power h, dh to the power d is nothing but d factorial times the volume of the corresponding polytope, if this is an ample divisor for dH ample. Well, if it's not an ample divisor, you'll need to say what the volume of a virtual polytope is, but this is also simple. So you have something defined on a cone, so you need to extend it as a polynomial to the whole space, right? Or well, you can, well, if you really want it, you can just struggle saying that this is some positive volume of some positive part with minus volume of negative part. But yeah, if you're in dimension greater than 2, I don't recommend that. So given this theorem, it turns out that we know what is this a to the power d map, right? So this just takes a divisor into the volume of the corresponding polytope. So theorem due to Pukhlikov and Khovanskii in this order because it's the order in Russian alphabet, and this paper was originally published in Russian. So this theorem tells you that the homology ring of a smooth toric variety is isomorphic to the ring of differential operators on this diff p sigma on the space of virtual polytopes modulo the annihilator of the volume polynomial. Okay, so here we are. So we give a transparent meaning to the to this ideal. So this is just the set of differential operators that annihilate the volume. And in a sense, you can view differential operators in facets as like infinitesimal movements along, parallel to this, perpendicular to the faces. So this allows you to compute things in the cohomology of a toric variety just by intersecting faces of the corresponding polytope. So what was our goal? Our goal was to generalize this to K theory, as I stated in the title of my talk. So here's I have like 15 minutes. Okay, so so our goal with Leonid Monin was generalize this to K theory of toric varieties and, well, eventually of flag varieties, because this story has a flag counterpart, and I'm going to briefly tell you about it if I have time. So so for this, I will need a formalism of rings with Gorenstein duality. Rings with Gorenstein duality. So let A be a commutative R algebra with the identity, and let L be some linear function from A into R. So this is an R vector space that it makes sense to say what a linear function is. And such a linear function defines me a symmetric bilinear form on my algebra. The form is as follows. So A, B sub L is just, well, I need to take the product of A and B and apply L. I'll get a number. So this is symmetric bilinear product. Bilinear form. And I will say that this is an algebra with Gorenstein duality if this product is non-degenerate. So if A, L algebra with Gorenstein duality if this is non-degenerate. Okay, and so our goal is to generalize this construction. So, well, this construction is a sort of a particular case because here this form was just Poincare duality on the graded algebra. This algebra is not graded anymore, but somehow I have a God-given symmetric bilinear form, which is non-degenerate. So I would like to view it also as some like differential or difference operators on something. This something will be a lattice. So I would like to view this as some algebra of difference operators on a lattice, and this will be as follows. So let me take a lattice, lambda, capital lambda. This is isomorphic to z to the power d, and let's say it's generated by some standard z, let's say n, u1, etc., un lattice. And I can view functions on this lattice, just arbitrary functions with no restrictions at all. So let g from lambda to r be any function. if I assume this is, well, I should assume that my graded, so yeah, if I have this construction, I have this one, right? But other way around, I think that you need to require like graded components are orthogonal, something like that. Yeah. So, yeah, so I'm not sure about that. Okay, anyway, so I have this function, and I can consider operators of shift. So let's say Ti applied to g of x is nothing but g of x minus ui. I just shift my function by this unit vector in the direction of ith coordinate. And Ti inverse g of x is gx plus ui. So I have these operators that act on my lattice, and they, well, I can take their products, I can take their linear combinations, so I get an algebra of shifts. So I'll denote it by shifts of lambda. And in a sense, it's nothing but a group algebra, but the group algebra of this lattice, right? So essentially, it's isomorphic to R lambda group algebra. So, but given a function, given an arbitrary function on my lattice, I can look at the elements of this algebra that make this thing vanish. So inside of it, I have the annihilator of G. Well, so a quick example. If my lattice is just integers, and if my function is constant, then if I just shift it to this or that direction, it will be equal to itself, right? So shift minus the identity is 0. So this is in the annihilator. So if I have an exponential, then shift equals this function multiplied by the exponent. And if I have, let's say, a polynomial, this means if I shift it and subtract it from itself, I get a polynomial of lower degree. These are difference operators. And so eventually you will also get something like in this case, that if you apply a polynomial in these shifts of sufficiently large degree, you'll get 0. So so for a generic G, so if I take my G like at random, most probably my annihilator will be 0. So for G generic, so this annihilator G0. But for interesting G's, it is not. So if like proposition, so if my G is quasi-polynomial, then AG is, well, yeah, and I didn't tell you what AG is, but you probably guessed already. So this is the algebra of shifts modulo the annihilator of G. So my AG is Artinian, like finite dimensional Artinian ring. Okay, so we would like to have a similar characterization, something like we had in this case. And here's our first result. So, well, first of all, given well, this construction, if AG is finite dimensional, it is a Gorenstein algebra. It is Gorenstein with where this L, this linear function is just nothing but the value of L function, L applied to T, to the shift operator T, is nothing but this operator applied to G and taken at 0 at the origin. Okay, so this is one direction, so this construction gives us something we expect. And then there is one more, well, there is the opposite condition that all of these are of this type. So let A be a commutative algebra, be commutative finite dimensional algebra, and a requirement is that A is generated by invertible elements, A1, etc., AS. A1, AS are invertible. With Gorenstein duality defined by some linear form with Gorenstein duality. L from A to R. And then A is isomorphic to AG, where G is the following function on a lattice, that you need to take an S-dimensional lattice where S is the number of generators, and the map is as follows. So given an element of this lattice, like K1, etc., Ks, you take K1, etc., Ks, you map it into A1 to the power K1, A2 to the power K2. These guys are invertible, so this makes sense for negative numbers as well. As to the power Ks, and apply L to it. Make sense? Okay. So yeah, this tells me that this construction really produces something valuable, and so like 2 minutes. Okay, so yeah, so I'll be brief about that. So for K theory of toric varieties, K theory of toric varieties, this is quite parallel to what we did for cohomology, but so we consider, instead of cohomology classes, we consider vector bundles, K naught of X, and vector bundles. And you just say that L1 plus, V1 plus V2, V3 equals V2 if there is an exact sequence, short exact sequence of such a form. And then, yeah, you can say that this is that K of, let's say, X sigma, toric variety, K naught of X sigma is generated by T equivalent line bundles, is generated by T equivalent line bundles. So like parallel, something parallel to divisors, right? So line bundles, a line bundle is almost the same as divisor. And bundle LH, which is O of a divisor, HIDI, is ample if it is some actual polytope of PH in the space of polytopes with a given normal fan. well, an integer polytope, right? Everything is integer in my in this case, and my theorem, well, our theorem with Leonid is as follows: that yeah, and so what's the map that brings a vector bundle to a number? It's the Euler characteristic, right? So so a well-known theorem is that chi of x sigma LH is the same as the number of points in PH intersected with D, z to the power n. And this is the same as, well, this is something called the Ehrhart polynomial. So for a given polytope, for given support numbers, you compute the number of integer points inside this polytope, and this depends polynomially of these x's, right? So this is the Ehrhart polynomial of, let's see, sigma of h1, etc., hs, whatever is the number. And finally, the theorem is that k of k naught of x sigma is the shift algebra on the lattice of integral virtual polytopes with a given normal fan modulo the annihilator of the Ehrhart polytope of sigma. So this is quite parallel to what we did in the toric case, but instead of the volume, you'll need to consider the number of integer points. So homology theory and K theory are similar, but not quite. One is a deformation of the other. One is like a non-homogeneous deformation. And how to get this instead of a volume, you'll need to consider something more subtle, which is the number of integer points. Well, one final remark is that, unfortunately, I don't have time to speak about that, but this has a parallel for full flag varieties, in our case of type A. We don't know about other types yet. But yeah, you can compute products of Schubert cycles and the corresponding elements in K theory just by intersecting faces on certain polytopes, namely Gelfand Zetlin polytopes, which will be, I guess, which will appear in the talk of Igor Machlin. Thank you. That's all for today.
Any questions?
First, do I understand correctly that quasi-polynomial is polynomial times exponent?
Say again?
So quasi-polynomial is defined as polynomial times exponent.
Yeah.
Yes. Then when you define G in your theorem, it looks like pure exponent.
It's what?
So when you define G map from K to L of A, it looks like pure exponent. Am I wrong?
It's pure exponent, yeah, but yeah, if you take like x times the exponent, you differentiate it, and you get something like, you get the Leibniz rule, so you need to.
Okay,
so yeah, I actually don't need the quasi-polynomial part. So we only working with polynomials, and we didn't quite look at the quasi-polynomials.
Okay. And then the other one is just like historical reference. I know about BKK, about mixed volume of polytopes,
right, yeah.
For number of solution of system of equations.
That's right.
If not K series, just on this language of toric varieties, what it corresponds to here? It's like several toric varieties intersect?
This is the intersection of several divisors. So yeah, here I'm well, historically Kiritchenko formulated his theorem in the following way. So suppose you have several equations with the same Newton polytope. So all equations have the same Newton polytope. Then the number of solutions is the volume, well, times some factorial. And of course, you can just extend this. Well, you probably want to solve systems of equations with different Newton polytopes. And this, yeah, this is how the notion of mixed volume appears. And in the language of toric geometry, this is just intersection of certain divisors, not just taking the power of one divisor here. And yeah, there you will get mixed volume indeed. Yeah.
And then this like homology ring, it will be like it like correspondingly you can define homology.
No. What is your embedding? Your embedding is defined by one divisor. And for this divisor, yeah, you have an actual polytope and its volume.
I mean, maybe the question, the dimension of some ring will be number of solutions. Is it somewhere close here or not?
Maybe, but I don't quite see how. Okay. Maybe you can make this meaningful, but I actually never thought in this direction.
Any other questions or comments?
Oля.
I just wonder, do you use the Riemann-Roch theory for computation of Euler characteristic?
Yeah, it's in a sense it's inside here. Yeah, the initial paper by Pukhlikov and Khovanskii was yeah, it had was Riemann-Roch in its title, and that's how you can find it. Yeah, it's hidden inside. Yeah.
Yes, and another question: what kind of singularity assumption on your polytopes? This is simplicial polytopes or
this is yeah, this must be polytope of a smooth toric variety, so it must be integrally simple. But as I didn't tell you, it also makes sense for certain non-simple polytopes such as Gelfand Zetlin.
Because as for non-simple polytopes, you need some mixed code structure. So cohomology of in the non-simple case involves some mixed structure. That means you have non-zero cohomology in high degree. For non-simple polytopes. If simple polytopes, all things okay. But for non-simple polytopes, there are some singularities.
I don't know how this works for non-simple polytopes in general, but like a homology of a single variety is like a subtle thing, right? So, I would say that for in some cases, like in the Gelfand-Zetlin case and some Gorenstein and Selivinsky polytopes, this works, but this is quite a mystery. So the toric variety behind is well, it's not smooth, but yeah, but still it corresponds to homology of something meaningful named flat variety. I'm not sure if I answered your question, but
okay, let us thank Evgeny again.